Hello and welcome to our TI Technology webinar hosted by Texas Instruments Australia. We are excited to bring you applications of integral calculus, Unit 4, Topic 2 from the QCE Specialist Mathematics course with a very experienced mathematics teacher and consultant and TI trainer, Mr. Frank Moyer. My name is John Bayman and I am your host for this event. I teach mathematics to years 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. Now, before we get started, I just wanted to remind you of the QCE teacher resource books, which are available on the TI Queensland website, which have been extremely popular, and the specialist one, obviously, Frank will refer to tonight. And if you don't have a hard copy yet, please email teacher-support@list.ti.com and they'll post one out to you. And to let you know, the General Maths Teacher Resource Book is now also available online as a PDF. As a general reminder, tonight's webinar is being recorded and will be available to rewatch or share on our on-demand webinar page on the TI Australia website. And please, I encourage you to send any questions at any time to Frank using the chat window on the right-hand side of the screen, and I'll get them answered for you. I now would like to introduce our presenter this evening, Mr. Frank Moyer. Welcome, Frank.
Great. Hi, how are you?
Very well, thank you. Great to have you with us. Frank has vast experience in teaching mathematics, curriculum development, and sharing his knowledge at national and international conferences. Frank is also passionate about rich tasks and the use of CAS to strengthen and deepen students and teachers, for that matter, understanding of various mathematical concepts. So thanks, Frank. When you're ready, we'll get your screen up and we'll share your screen. That is perfect. We can see QCE Specialist Maths on the TI-nspire teacher software. So it's all yours.
Okay. Thank you, John. Thank you for that introduction, John. And welcome, everyone. Thank you for joining us. Now, as John said, tonight's webinar we'll draw on material from the QCE Specialist Maths Teacher Resource Book for the TI-nspire CX2T, which consists of 166 pages of learning activities, which all include detailed step-by-step instructions. Now, the focus of tonight's webinar, has already been mentioned, is applications of integral calculus. In particular, we'll be looking at multiple representations for bounded areas, volumes of solids of revolution about the X or Y axis, 3D graphs for surfaces of revolution, Simpson's rule, and looking at the effect of changing the interval size on the accuracy of the approximation, and probability density functions for an exponential random variable. If time permits, we may also have a look at something which is vaguely related to the exponential distribution from the simulation, which is from topic 5, but it mainly focused on topic 2 tonight. Okay, I'd just like to mention also that the teacher resource book, many of the activities focus on using the technology for teaching and learning maths, not just for doing maths and answering routine questions. So it aims to leverage the dynamic features of the technology for powerful visualization of concepts, use multiple representations for exploring connections between concepts, which will hopefully result in greater clarity and deeper understanding of the maths for students. Okay, so let's make a start with bounded areas. So we're looking at the area bounded by the function f, the function g, and a lot from interval from -3 pi on 4 to pi on 2. And we're going to do that, first of all, in the graphs application and then in the calculator application to have a look at the multiple representations of the problem. Now, the page that you see before you is a notes page, and the notes page, if you just start typing, it's just like writing in Microsoft Word or similar. But once you insert a text, a maths box, which you can do by pressing Control M, that's the shortcut, then you can perform calculations the same way that you would on a calculator page, but with the added benefit that the text, the maths box is editable. So here, if I want to change that, if I want to define that function f, I can just insert an assign and press enter, and that problem 2, throughout problem 2, the definition of f of x will be understood. Likewise for g of x, we'll define this function. Okay, so let's start looking at the bounded area between those two graphs. So to save time, I've already adjusted the window, and with the window settings, I've used an exact value for the x scale, and that should enable an exact value to be displayed. If you've got the CX2T and you're only getting a rational approximation there, then perhaps you need to adjust your document settings. So the shortcut to document settings is just click the battery icon, document settings, and just make sure that down here where it says exact arithmetic, make sure that that has been enabled. Also, if you want to show multiple labels, just hover over one of the ticks on either axis and get the context menu, control menu, attributes, and down here you can either have single or multiple ticks. So I want labels rather, so I want multiple labels. Okay, now because I've already defined f of x and g of x on this page, I can graph by just having f of x for f of x1 and likewise g of x. Now, if I also want to put in the line x equals negative 3 pi on 4 and x equals pi on 2, I can do that in a number of ways. One is to just hit the delete key, and it gives you various options. If you go to option 6, you can enter a relation. So we're going to do enter x equals negative 3 pi on 4 and x equals pi on 2, which you can either press the button, or if you're doing this on the software as I'm doing, you can actually type in the word pi. And I'll move these out of the way. Now, for the bounded area, if I want to do it in one go, menu, analyze graph, bounded area, in one go. If you hover up to the tool on the top left-hand corner, you see that it tells you what to do. Click the two functions, then click the bounds. So I want these two functions, a bound here, that intersection point, and at that intersection point. And I get a value of 3.33. Now, the reason it only displays 3 digits is because of the settings. So you can go menu, number 9, settings, and you've got the graph and geometry settings, which are separate from the overall document settings, and it's set to float 3. Now, I usually keep it at float 3 because I don't want a lot of digits cluttering up the screen. But if you want to display more digits, you can just hover over the value and just press the plus key. So when you press the plus key, it will display more digits. If you hit the minus key, it will display fewer. If you want to sometimes you might want to find the individual areas, so up to this intersection point here. By the way, just a few tips on finding intersection points. To find intersection points, there are at least 3 ways you can do it on Inspire. The method that I use the least is going through Analyze Graph and Intersection. I find that rather cumbersome. If you want multiple intersection points, then I think that the quickest way is to go Geometry, Points and Lines, and Intersection Points. And up here it tells you what to do. Just click the first graph, then the second graph, and you instantly displays both of the coordinates of both of the points of intersection. If you want more digits, again, you hover over a particular number and just press the plus key. Now I'll undo that. Control Z or Control Escape. Another way of getting intersection points is with the point tool. So all you need to do to access that tool, the shortcut is just press the key for the letter P, and you get those 2 options. So I want option 1, and you just hover over the intersection point until you see intersection point displayed and click. So when I only want a single intersection point, that's usually the method that I use. Okay, so if I want the individual areas, then Analyze Graph, bounded area from these 2 graphs. It gives me that one, and I can repeat the same thing for the other piece. Click those 2 and between those 2, and you've got the 2 individual areas. Okay, so let's do the same thing in the calculator application. So I'll add a calculator page, and this time I'm going to find the point of intersection using the numeric solve. So I can either access that by going to algebra and numerical solve, or if I wanted to know what the syntax is, if I wasn't sure about the syntax, I could go to the catalog, press the catalog button, press O, go to numeric solve. Now the end solve, the syntax is equation and then the variable, and you've got the option of putting in equals a guess. And I think that that is really useful in a case like this. So I want to know where the function f of x is equal to g of x, and the variable is x, and I'm going to guess that it's somewhere, let's go back to the graph, it's going to be somewhere near negative pi on 2. So let's put that in as a guess. Whoops. Oh, I see what I've done. Okay, I'm in a new problem, so therefore it didn't recognize f of x and g of x. So I'll redo that. I'll just copy this. So that was f of x.
And Frank, that's because you opened up a new problem. So it's 3.1 and 3.2, not a new page. Is that the reason?
That's right. Yeah. So I I did it in a new. Okay. So let's go back. I'll go back here. I should have opened my. I'll start again. I'll open my. I'll add the calculator page here. Okay, let's start again. So nsolve, and it's f of x. So here I do have f of x. I should have noticed that. Well, I noticed that now the f is bolded. The f wasn't bolded because I'd added the calculator page to a new problem.
And I suppose also if they press the var button, that would also show you what variables that you have access to.
Exactly. I should have done that. Yes. So
So should your
in
host,
my haste,
Frank, so don't worry too much.
Okay. All right. So so that illustrates the difference between adding a page and adding a problem. So I should have added the page to the existing problem, not to a new problem. Okay, so now let's do the numeric integral. So the shortcut to the numeric integral, just shift plus, and I want to go from negative, I think it was 3 pi on 4, and I'll just type in pi because I'm doing it on the software, to this value up here. So I can just grab that value, or else I could have saved that as, say, x1, and then just typed in x1 there. So now if I don't want to be too bothered about which one goes first, the F or the G, I can, of course, go to the templates and choose the absolute value, and f of x minus g of x. And I can do the same again, except this time I'm going from the intersection point. Whoops. Try again. I'm going from the intersection point, which is negative 1.0728. That'll be enough. To pi on 2. And I get my other area, then I can add up the two areas. And I get the same result as I did when I did it graphically. Okay. Okay. So, from bounded areas to volumes of solids of revolution. So what I'm going to do is set up an editable interactive notes page to calculate volumes. Now, when you set up a notes page in this way, you can save the notes page. You can even save it into the My Widgets folder, and then you can open it up in any document. And you can keep reusing it. You save it whenever you need it. You just open the document and reuse it. You edit the inputs. We're also going to graph the region to be rotated and the 3D graph of the surface of revolution. Okay, so in this problem, we're going to find the region bounded by the x-axis, f of x equals cos x, between negative 7 pi on 16 and pi. So rotation about the x-axis. It's going to be the integral from a to b of pi f of x squared. So it's the analogous to volume equals. So analogous to the pi r squared. So to set up the notes page, this is where I'm going to be able to edit the function in the maths box. Now, in this case, it was just fx equals cos x. F of x, I'm going to assign cos x. Now, the lower bound, I'll assign oops, wrong one. That was negative 7 pi on 16. The upper was pi, so I'll call that B. And the volume, I'll just copy the formula. If you're doing this on the, if you're copying on the handheld, by the way, you just hold down the shift key and just arrow across. That's the quickest way to select on the handheld where you don't have an external mouse. So I'll copy that, Control C, and over here, V, assign, and I'll paste that. No, it doesn't want to paste. Let's try it again. Control C, and I'll Control V. That's better. And it's given me the volume of revolution. So if I was to change that, for example, to sine of 2x, it would recalculate the volume. Or if I was to change the edit the terminals, it would also change. Okay, so it's probably useful for students to be able to visualize what it is that's being rotated. So rotating cos x and the domain restriction. So Control equals, choose the given from negative 7 pi on 16 through to pi. So that's what it looks like. Now, it's probably useful if that's shaded so that students can visualize what is being rotated to form the solid. So we could do that with using the integral under Analyze Graph Integral. And now I have to choose a lower bound. Now, before, to get the lower bound, I actually had the line x equals something. I can do it that way, or I can just start typing the value in. So if I start typing negative 7 pi on 16, that's locked in the lower bound. The upper bound was pi, so just go and input pi, and the actual value of the integral is not significant. What's significant is that students can visualize what it is, the region that is being rotated. Would be even more useful if they could see that in 3 dimensions. And the TI-nspire has the ability to do that. So to do a 3D graph of the surface of revolution, we just need to know a little bit more maths. So if y equals f of x over the interval AB is rotated about the x-axis, the surface of revolution has parametric equations. Obviously, x equals t, y is f of t times the cos of u, z is f of t sine of u, where t is an element from A to B and u is 0 to 2 pi because it's got to be rotated right round in a circle. Now, to get the 3D graph, I'll add a graphs page, and this time I'll make sure that I add it to the existing problem. And to get 3D graph, it's under view. So I'm going to, so this is a graphs page, and if I go menu, view, 3D graphing. Now the default entry is to do a z as a function of x and y. I don't want that. I want to enter a parametric equation. So to enter a parametric equation, I can go menu and go to 3D graph entry edit and choose parametric. Then I can start putting in my parametric equations. But before I forget, I'm actually going to put in my parameters. I'm going, over here where you've got those 3 dots, you can edit the parameters. And I'm going to do that first because I tend to forget otherwise. So the value of t is restricted from A to B. So that's from negative 7 pi on 16 to pi, and u right round the circle, so from 0 to 2 pi. Now I can start putting in the parametric equations. So x is just t. Now the y is f of t, and yes, I can see the bold f, so I know that I'm in the right problem, not making the mistake I made earlier, times the cosine of u, and f of t times the sine of u. And what have I done wrong? I've obviously put in incorrect parameters somewhere. Negative. And that's pi. Ah, okay. Let's see what I've done wrong. Okay, this is one I did earlier, so I've got the same parametric equations, f of t cos u, f of t sine u. I've got the same parameters. Okay, so I can't see what I've done wrong with the other one, but obviously I had too much. Now, there's a few other things I should mention. So that's putting the parameters in and the equations. I can't see what I must have typed something in wrongly in the other one, and I can't see what it is. Now, a few other things that you need to do to make it look like that. You go range zoom, so the range settings. So I set the range settings from so that they were just a little bit greater than the graph. So for example, because I was graphing a cos function, which has an amplitude of 1, I made the y and z range values from negative 1.1 to 1, negative 1.1 to positive 1.1. Now, the other thing to do is if you want to magnify, you repeatedly hit the multiplication button, will enlarge. If you hit the division button, then it will reduce. So you can zoom in or out with the multiplication and division button. A few other things you can do. If you just press the letter A, it will auto rotate. That's a shortcut for auto rotate. And you just escape to stop the auto rotate. You can also rotate by hitting the left and right, up, down arrow keys. So it's easy to visualize the 3D graph. Okay, so rotation about the y-axis is much the same. So I'm rotating y equals x squared minus 4 from y equals negative 4 to y equals 5. Now, once again, if x equals g of y between a and b is rotated about the y-axis, then the parametric equations are similar to what they were, except that this time it's y that has the parameter t, x has gt of sine u, and z gt of cos u. So that's a graph. That's the region that's going to be rotated. I could have had the other half. I could have had the negative half. It'll still be the same solid of revolution when it's rotated about the y-axis. So in this particular case, I've set up the notes page. This notes page is editable. So if, for example, I had chosen the negative square root, note that the volume doesn't change because it's still the same volume of revolution, irrespective of which half you choose, which half of the parabola. And now this time, the graph entry edit, I chose parametric. So I entered the parametric equations, gt sine u, t, and gt cos u. Now, I set the parameters from negative 4 to 5 and from 0 to 2 pi. And once again, if you press the A, you can auto rotate, or you can rotate manually, or you can just grab it. So to grab, by the way, I'll escape. To grab on the handheld, it's control and hit the click, or just hold the click down for a second or two, and you can grab it and rotate it that way, or you can use the keys. You can arrow keys to rotate. Okay, so that I think is quite useful for visualizing what's happening in 3 dimensions. All right, so that's solids of revolution are about the X and Y axes. It's just a matter of entering, and for the solids of revolution, entering the parametric equations correctly. For some, I must have entered something incorrect, but I wasn't going to waste time checking what I typed in correctly. Okay, Simpson's rule. So Simpson's rule is a method for approximating the value of a definite integral using parabolas to approximate the curve. So Simpson's rule generally gives a more accurate answer than, or more accurate approximation than, say, the trapezium rule, which uses straight lines to approximate the curve. And in fact, Simpson's rule gives an exact value, not just an approximation, when the function being integrated is a polynomial of degree 3 or less. Now, it's pretty obvious why, if you had a quadratic polynomial, why, if you were using parabolas to approximate the curve, why you would get an exact answer. It's not so obvious why it also works with cubics. And I guess the derivation of the formula is beyond the scope of the syllabus, but it relies on looking at the error term formula. So the error term formula comes from the theory of polynomial interpolation and Taylor's theorem. And what it does, and this is the bit that students can understand, that the error term formula indicates how far off the approximation is based on the fourth derivative of the function. So with a cubic, the third derivative of a function is obviously a constant term. The fourth derivative is 0. So invariably, for every cubic polynomial, Simpson's rule will give an exact answer. Simpson's rule sometimes also gives an exact answer for particular functions, but that's just because they happen to integrate in such a way that the errors cancel each other out. Okay, so how does Simpson's rule work? So we take an interval AB over which we want to integrate and divide it into m subintervals. So I've called, in this case, for example, we've got 4 subintervals, so I'm calling that m equals 4. Now the boundaries, I'm calling the value at this boundary x1. So A is also x1. Now I know that many authors prefer to call that boundary, that end value x0, but as you'll see in a minute, I'm going to use a sequence command to generate a list of these x values, x1, x2, x3, and I think it's more intuitive for students if the first term of the sequence is x1, the second term is x2, and so on. So that's the reason that I've chosen that convention. Okay, now the width of each subinterval, which I've called W, is obviously B minus A divided by M. And the formula for Simpson's rule, just go to the end here. There you go. The integral from A to B of f of x dx is approximately the subinterval width divided by 3, and then you've got the f of x1, f of x2, f of x3, up to f of xm plus 1, if you use my convention, with the coefficients going 1 for the first and last term, and then alternating between 4 and 2. So all the even terms are 4, and the other terms are 2. So the coefficient list looks like something like this: 1 at the two ends, all the even terms are 4, and all the odd terms are 2. And that's significant when I automate creating a notes page for Simpson's rule. Okay, so in this case, I want to approximate the integral from 3 to 4. In fact, in this case, because it's a cubic, it's in fact going to be an exact answer. So from 3 to 4 of x cubed minus x plus 1. And this is in a text box, so if I press enter, it will actually evaluate that integral, and it's 41.25. Now, I'm going to use Simpson's rule with m equal to 4, so I'll change that to an assign rather than an equal. So that's now stored as m. And f of x is this function here, so I'll just copy that, Control C. So f of x, I'll assign no, didn't copy it. Try again. So it's that one, Control C and Control V. This time it's worked.
And Frank, those are coming up as blue because you've got them inside a maths box. Is that correct?
That's correct. So once they've been evaluated, then they appear blue. That's correct. And that's one way that you know that it's a mathematical expression in a maths box rather than just text. So A, I'll assign 3, and B, I'll assign 4. So the width, now in this case, it's fairly trivial, but the point is that I could then, I can set up a page which I then edit and it will recalculate. Okay, so this time I assign the width as, obviously the width is going to be 1 over 4, so it's going to be 0.25. So 0.25. So the width is going to be 0.25, a quarter in this case. Now, f of x1, I've already defined the function, so I can just substitute in the value. So the first value, my x1, is just the value of a. So it's a plus no width. So it's just the value of a, which is 3. x2 is my initial value, 3 plus 1 width. So it's 3.25. The next one is going to be the initial value 3 plus 2 widths, so 3.5. And plus 3 widths. And the last one, obviously, it's 4. And I get 41.25, which is the exact answer, as I would have expected, given that it's a cubic, and we know that for cubics it gives an exact answer. Now, that's a bit cumbersome doing it this way, so you can automate it, and it takes a little bit of time to get this going, but once it's set up, it's one that you can just keep using. And in fact, if you save the notes page as a widget, then you can open it in any document. You don't have to open it as a separate document. Okay, so we want to find the area under the graph of sine x e to the 2x from 0 to pi, and that's the value. So it's roughly 107.3. So we're going to have a look at how close Simpson's rule gets for different interval sizes. So we're going to create an editable Simpson's rule template, and we're going to explore the accuracy for subinterval sizes from m equals 2 to m equals 20. So let's have a look at what this function looks like. So we can see that approximating that with parabolas, it's not going to be just having two intervals is probably not going to cut it. You're not going to get a very good approximation. Okay. To set up the notes page, there's a few commands that teachers may not be familiar with. We're going to generate a sequence of, first of all, coefficients, and then the interval boundaries xn. So the command that I'm going to use is the seqn command. Now, the reason for choosing that when you go to the catalog, if you have a look at the sequence commands, there are three sequence commands. There's the seq, seqn, and seqgen. And the reason I've chosen this one is because of the simplicity of the syntax when you have an explicit rule. So if I have seqn of n squared comma 5, it will return the square of n equals 1 through to n equals 5. 1 squared, 2 squared, 3 squared, through to 5 squared. If I change that to 3, it returns the square of the first 3. The other thing is, I want to be able to select the even terms in the sequence, because when I'm selecting coefficients, remember that all the even terms of the sequence have the coefficient of 4. So a command I can use is the remain command. So remain, if I have a number, comma 2 equals 0, it's saying that number, n, when I divide it by 2, the answer is 0. It's true. If the value of n is, say, 7, it's false. So it can choose whether a number is odd or even just by using that simple command. All right, so to create this coefficient list, it either has to be 1, 4, or 2. So what I've done here is, in a maths box, I've got the piecewise function template. So I want this to generate 1, the sequence to contain 1 when n equals 1 or when n equals n plus 1. In other words, when for the first and last term. I want it to display 4 when the term is even. In other words, the remainder of n comma 2 equals 0. The rest of the time, I want the coefficient to be 2. Now, to generate the sequence of xn values, the formula is very simple. It's just the initial value, the n value a, plus the number of widths n minus 1. So x1 is just a, x2 is a plus 1 width, x3 is a plus 2 widths, and so on. So it's always n minus 1. So I'm going to apply those commands to set up my template. So let's do the function. So it's Control M to get a maths box, and I'll just copy the function just to make sure that that it's sin x. So I'll copy and paste it, make sure I don't get it wrong. No, it's not pasting. Okay, let's do it again. I'll just Control C. There we go. Now the A value, so okay, so A I'll assign, that was 0. And my B value was pi from memory. Yep, it was 0 to pi. Now, the intervals, I'm going to change the number of intervals. So I'll start with 2. What have I done? What have I done wrong? Oh, I see.
Equals,
I put equals instead of a sign.
sign.
Yep, a sign. Okay. Now, the interval width. So W, I'll assign. Now, it's going to be B minus A on M. And, of course, M will vary. Now, my coefficient list. So I'm going to use the seqn command. So I'm going to select that sequence. Now, the expression that I want, I actually have over here. So it's this expression here. I want it to generate 1 or 4 or 2, depending on those conditions. So I'll Control C and I'll paste it here. So they're the conditions. And I want it to go from n equals 1 to n equals m plus 1. So you can see that it's generated 141 because I had m equals 2. If I was to change that to, say, m equals 6, then we see that it's come up with the new list of coefficients.
And Frank, with this document like this, teachers could have it already prepared if they wanted to, and then either show it on their screens or they could actually share it with students to use as well, couldn't they?
Absolutely, absolutely. And in fact, I think that this one is probably one that is more for a teacher to generate to give to students rather than one for students to do themselves. Okay, so the X list. So let's go back here. The X list, this is I just want A plus W times M plus 1. So I can once again use my sequence command. So I want a sequence. So that's the formula. W has been assigned, A has been assigned, so it should work. And I want to generate that through to M plus 1. So it's generated those values. And of course, if I was to change the number of subintervals to, say, 10, you can see that the interval width changes, the coefficients change, and those values change as well. Now, the F list, the list of F values, what will I call that? I might call that F values, FVAL. So, and I'll assign that F of this list here. Now, I haven't given this list a name, so I better give that list a name. I better call that, say, XV for X values. So XV, I'll assign, so that's the list name. So that list is now called SV. So if I select from the var XV there, it looks pretty ugly. So I can either say approximate value, I can change the document settings, or even easier than that, I can just multiply by 1.0. And once there's a decimal point, it will give an approximate answer, a rational approximation. Now, the other thing I should do back here, I should give there's another list I haven't given a name to. So the coefficient list, perhaps I'll call that coef. So I'll call that list coef. So hit the assign.
And Frank, we could change the view from document preview to computer preview, which would give a different, not a calculator style, but it would give a bigger screen for students to see as well, wouldn't it?
That's right. So if for a teacher demonstration, you could do it in computer. The reason I'm sticking with handheld view is that the teacher resource book is intended for the handheld. So everything should work on the handheld. So I'm sticking with so that it looks the same as in the teacher resource book. But absolutely, with computer view, you would see a much, you get a better perspective, no doubt. Okay, so all I have to do now to work out Simpson's formula, I've got the formula there for Simpson's rule. So I'd better give that list a name. So I might call it simp. W is defined, and I want the sum, the coefficient. Yes, I've got all the coefficients. Now this f of xn, I actually call that f val. So I'd better change that to f val. So I'll choose it from the var list. And what have I done wrong? What have I done wrong? Let's go. Let's have a look.
Was it in the maths box there, Frank?
Should be in a maths box. It worked. Yeah, it's in a maths box. Simp defined as W over 3 times the sum of the coefficient times, I think I called it coef, didn't I? Yep, it's bolded. Ah, okay. Oh, here it is. It's exactly the same. It's just that this time I just gave that list a slightly different name.
Was it the brackets around the maths box that didn't help?
No, it's exactly the same. Oh, I don't know. Okay. I won't dwell on. Anyway, it's the same thing. So all I've done is I've called this simp val instead of simp, W divided by 3, and I've put a decimal point to make sure that I get a rational approximation. That might be the problem. Perhaps it didn't like the fact that it was a big. No.
See how there's a bracket before simp and after.
Oh, I see. Yeah. I see what's wrong. Yes, it's in a bracket for some reason. Yeah. Okay. X. Okay. Not sure. Try it. That's it. Whew. Okay. Yeah. So thanks, John. Yeah. It's just for some reason the whole thing ended up in a bracket. Okay. So we what would be useful now would be to have a text box control. So have the M value closer to the answer. So when I have two intervals, the answer is just over 48. So that's pretty hopeless. That's not even close. However, as I increase the interval size, let's try 6, 105. Remember, it was 107.3 was the actual answer for the integral. So let's do 10, getting closer to almost 107. Let's do 20 intervals, and it's 107 point, pretty much almost spot on by the time you've got 20 intervals. So what you can do is capture, what I've done here is I've captured the values. I've called this list intervals and this list the approximation. And what I've done is I've captured M in this column, and in this column I've captured the values of the Simpson's rule approximation. And every time that I entered a new value, it's populated the spreadsheet. So I can now put in a data and statistics page, and I press Tab and I select the intervals, and Tab again and select the Simpson approximation. And I can see that it's that it converges, it very quickly converges towards the actual value. So I can go Menu, Analyze, Plot Function. Now the value was about 107.3. So we can see that it converges pretty quickly, even for a function such as that one. All right, now I think that my hour is over. So I might leave it at that. And thank you very much for your attention, and thank you very much for your patience, and apologies for the fact that I did make a couple of inadvertent errors, but thank you very much for listening.
Frank, like all of us, we occasionally in the classroom make a few boos, and I thought the way you recovered those and showed us where those errors were, but also the calculator helping us work what they were was fantastic. So thank you very much. And as some of our participants said tonight, there's a lot to think about here. Some fantastic concepts, not only for teachers to deepen their understanding, but also for them to share with students. So I think that the on-demand version of this webinar will become very important. So Frank, thank you very much for that indeed.
Pleasure.
So just a reminder, our dedicated Queensland TI education page can be found at education.ti.com/Oz/Queensland. And if you scroll to the bottom of the page, you'll find the downloadable teacher resource ebooks. And as I mentioned, if you go to the teachers section and go to PD, you'll find all the past on-demand webinars. So we're going to begin wrapping things up. If you do have any last-minute questions, please go and get those asked in the chat box, as I know Frank will endeavour to answer them or add them to planning for future webinars. And when we leave the webinar tonight, a brief 4-question survey will automatically appear in your browser. Your feedback guides us as we plan future online events. We will listen to your feedback, and so we hope you share your thoughts in a post-webinar survey. And if you're watching live in the next 24 hours, you'll be emailed a link to the past PD events. I also encourage you all to check out our student, or teacher for that matter, online courses and our very own TI dedicated YouTube channel. And that brings us to the end of our webinar. Thank you, Frank, for everything you've shared with us tonight. I've really appreciated it, and I know that our viewers have too. So thank you, Frank.
Thank you, and thanks everyone for listening. Good night.
And thank you everyone for joining us. Without you, there's no point in doing this. So we really appreciate you tuning in live tonight, and also watching it on demand in the future, and I hope you and your students benefit from it. And we hope to see you back online again soon. Thank you for now, and goodbye.
Bye.